Hello, my name is Bradley Van Dam, and today I'll be doing exam for chapter 29. And I'll be doing questions 8.1 through 8.4. So let's get started. So for 8.1, we are given the following information. What is it? A y with radius 2.4 centimeters lying on the xy plane. Two different uniform magnetic fields. It changes at a steady rate from 0.14 Teslas in the z direction at times equals 0 to 0.110 Tesla in the negative z direction at 2 seconds. So this problem wants us to find the magnetic flux through the loop at time equals 0, and then part B is asking for the magnetic flux to the loop at time equals 2 seconds, and part C is to find the magnitude of the induced EMF in the loop while the field is changing. So let's first start with part A. So we're looking for the magnetic flux. So let's call this, so in the problem they refer to as PHY2049. So that's what we're going to be looking for. So we can use the equation equals B and times the cross-sectional area, so I'll say B1 and then cross-sectional area, but we can represent cross-sectional area in this case to be pi r squared. So we're going to be left with B times pi r squared. And so we are given, I'll actually write out the little givens above here. So the wire is, actually instead of centimeters, I'll say 0 to 4 meters. B1 at time 0 is 0.14 Tesla. B2 at 2 seconds is 0.11 Teslas. And this is in the positive Z, and this is in the negative Z. And yeah, so we're given, so I'll say it's time is 0 times 2. So we're going to continue solving for magnetic flux here. And so since we have our initial uniform magnetic field of 0.14 Tesla, we can, and the radius, we can now solve this problem. So we can do 0.14 times pi times our radius in meters, 0.024 squared. That's going to give us, pi is going to give us 2.53 times 10 to the negative 4th, and that is in units of Webers. So that is 4A. And then part B wants us to do the exact same, but for the magnetic flux through the loop at time equals 2 seconds. So let's do phi2 like they said in the problem. And again, the same thing, but now we're just going to use our B2. Again, we can just rewrite that again as pi r squared. So the only thing changing here is that I'll just say ... because we're going to be doing the same calculations as we did for phi1 as phi2, but we're just plugging in different B values. So all we can do up here is just go back. Oh, and also we have to plug in negative 0.11, so it's in the negative z direction. So we're going to get a negative value for magnetic flux. Negative 1.99 times 10 to the 4th. Or 10 to the negative 4, sorry, Webers. Part B. And finally, for part C, we are solving for the magnitude of the induced EMF in the loop. So EMF equals, just say this would be negative, and then the change in phi over the change in t, and we're looking for EMF. And so we have the difference between the different magnetic fluxes between the two different times, and so it's going to be, so it's negative, and then second is negative 1.99 minus 2.53, which is multiplied by times 10 to the negative fourth, and that's divided by 2 minus 0, or just 2, and that will give us, let's plug that in. So we have two negatives, so negative out in the front, then 1.99 minus 2.53, close parentheses, times 10 to the negative fourth, and that gives us 2.26 times 10 to the negative fourth, because you have the negative there and negative there, those two cancel, we get a positive EMF value of 2.26 times 10 to the negative fourth, and that's going to be in units of volts. Part C, so that's all of 8.1. Let's go to 8.2. So 8.2 has two different parts in it. We're given circular coil, so turns, so it makes N equals 455 turns of wire radius 5 centimeters, so that many meters, with a resistance of 14.5 ohms. The area of the vector of the coil points in the positive z direction, and let's see, the coil in the region of uniform magnetic field points 20 degrees, from the positive z direction, so we'll say theta equals 20 degrees. And then we're given magnitude of the field is initially at, so I'll say BI is initially at 0.06 Tesla. And then it gives us the rate in which it decreases. So we're given the rate of change, so dB over dt is equal to -3 times 10 to the negative thirds, I believe it was. Yeah, negative thirds Teslas per second. And the question for part D wants us to find the magnitude of the induced EMF. So here we can use this equation here. So for EMF, that's what we're solving for, and we are given the rate of change, but we can actually rewrite that. So we're given the negative rate of change, or actually, no, we're not given the negative rate of change. We can use this equation where we use flux at change time equals negative, it's negative, and we can transform this EMF equation, since we weren't explicitly given the dphi over dt, and we can translate that to be d over dt multiplied by the number of turns times b times cross-sectional area A times cosine of theta. And we can further transform that so that we don't have to use the cross-sectional area. We can just transform that again, similar to the prep up here. So we have, now we're going to have -n pi r squared cosine theta. And we can actually, so we can move this over here. Since we have dB over dt, we can actually move the b to that numerator, and so we will have multiplied by the change in what is it? Change in field. So that would be dB over dt. And so now we have all the components here, and so we can actually start plugging in. So that is going to equal negative 455 times pi r squared and radius 0.05 squared times cosine of 20 degrees and then times the rate of change, which is negative 3 times negative 3 times 10 to the negative third. Since we have a negative here and a negative rate of change, we're going to get a positive voltage for our, I'll actually just put it down here since it ran out of space. Okay, so we're going to get a positive value for our voltage, so negative 5 pi squared times cosine 20 times and that gives us, let's see here, gives us 10.01. I'll round that off to do 1, 2, 3. Yep. So I could do 10.1. 10.1 times 10 to the negative third voltage or volts. And that is for part D. Part E wants us to find the magnitude of the induced current in the coil when the field is changing. So we can use this equation. So induced current, EMF over resistance. And so we're looking for I here. And we have, let me double check here. Yep, so we have everything. We just solved for EMF. So we have 10.1 times 10 to the negative third over given resistance, 14.5 ohms. .97 times 10 to the negative fourth amps is going to be the induced current. Yep. And that is part E. Let's go on to 8.3. Two-potter here again. So we are given, let's see here, square single loop of wire, 4 centimeters. Okay, so we have, radius, 4 centimeters. And that is on the XY plane. That's important. Number of turns again, so N equals 875. And then we are given, let's see, an initial and a final magnetic field. So I'll say BI for initial. We're given different directional components for it. So we have, so BI is at time 0, and that is 0.2 I, or I'll say, should I do, sure, why not? Let's just do that. plus 0.15k Tesla at time equals 0. And the final magnetic field at time equals 3 seconds, which is, let's see here, 0.3, oh, minus 0.2k. And so the problem is asking for the magnitude of the induced EMF in the coil. So for this, we can use this equation right here. So EMF, again, is what we're looking for, equal to N, change in magnetic flux over time. We can, let's see. Yeah, so this is, we can just rewrite this to be equal to N times change magnetic flux over time. But we weren't given this in the problem, so we're going to have to actually solve for that independently. So I'll just do a little square and a little arrow. So this guy over time, so we use a different equation to solve for this guy, is equal to field change in time multiplied by the cross-sectional area. And again, we're given radius, so let's just rewrite that to be change in B over change in T times pi r squared. But we also don't know delta B over delta T, so we're going to have to do another split off here. Another little side guy. Or sorry, not both of those together, not just a single one of the arguments. Just delta B, because we know the change in time, it's from 0 to 3 seconds, so just want to look for delta B here. And we're going to quite simply just observe the differences between the initial, or the final and the initial fields here, so we can write out the different components, and I'll just do it like an addition problem, or I guess in this case I'm subtracting them just to see the difference. Plus 0.2k, and again these are all in units of Tesla, so I don't need to go and write that out. 0.2 I minus the 0.15k for the initial. So we have, I'll just write in parentheses, BF minus BI, which is essentially the delta B. That's essentially what it stands for. So we're gonna get 0.3 minus 0.2, which is 0.1, and then 0.2 minus yeah, so minus okay, yeah, 35k. Make sure I wrap that. Yep. Okay, so that is this guy, and so now we can start working our way back up. So now that we have delta B, we can plug this in. So we have 0.1I minus 0.35k all over 3, and that is multiplied by, and again this is important why we noted which plane the radius was on of the radius of the wire. So we have let's see, pi r, so that's going to be 0.04 squared this guy, and that's in K. So let's see. Yes, so the only matching guys here are K and K, so we're gonna not associate with the I. So we go to have negative 0.35 times, and then that's just what, 0.001616, all divided still by 3. And let's put that in the calculator. And that gives us 0. Let's see what that is. Times 3. Okay, so it's going to be negative 1.87 times 10 to the negative 4th per second. And this guy, I didn't write the units over here, but that's in, kind of assumed we were doing that in Teslas. So then we got this guy, and now we can actually finally answer the original problem here, which was asking for the induced EMF in the coil. So this is equal to negative 875 times negative 1.87 times 10 to the negative 4th. So those both are going to cancel out. We're going to get a positive voltage. Then we get 0.163625. So I'll do 4. So 1636 volts, which is our final answer for part F. And part G wants us to find the direction of the induced current in the coil as seen from a point on the positive z-axis. So from here, since we are going the positive z-axis, since we're going from a positive to a negative z value, we can deduce, so we can say it's going to be counterclockwise, because, so counterclockwise, since BZ goes from positive to negative, and then we can say also using our right-hand rule. Oop. G. Now we are on to 8.4. I think this is another two-parter. Yes, okay, so we have this one doesn't give us actually explicit values. It's just in terms of different, they're just given like different variables for it. So, excuse me. So we're given a coil with area A. So A, number of turns N. Turns Y lies in the XY plane. Positive Z direction. And we're given, so it is exposed to a uniform time-varying magnetic field, which is, again, positive Z equal to, parentheses, B naught, sine of omega times t, close parentheses, and then in k, where omega is a positive constant, and it says to find the induced EMF in the coil, and our answer should be in terms of cross-sectional area A, turns N, B naught, T, and constant omega. So again, we can use the same equation here. So the only thing different is that we actually don't have explicit values. So equals negative number of turns times d phi over dt, looking for EMF. And so let's, okay, so we can say, in our case here, our phi is equal to B naught times area times sine of omega t. And so from that, we can rewrite our equation solving for the induced EMF to be negative N times d over dt, and substituting this in, so then we have B naught A sine omega t and we can just rearrange some of the information we have. So let's draw it down here. Negative N B naught times area d over dt still, and then again multiplied by sine omega t. Let's see. Yeah, and so that would actually just simplify down to negative N B naught A times, well, essentially, since we're doing, so we just do the derivative of sine omega t, so that's just going to be the derivative of sine is cosine, so then we're left, this is just, instead of sine omega t, it is now cosine omega t, and since we were given no explicit units, that is our final answer for the induced EMF in terms of the units they gave us for part H. And this one is for part I. It says to find the direction of the induced current in the coil as seen from point on the positive z-axis at time equals 0 to time equals pi over omega. So let's do both test cases here. So at time 0 and time equals pi over omega. So we have cosine of omega t. So if we have at time 0 cosine of omega times t equals 0, and that is just going to be cosine of 0, which is 1. And for pi over omega, pi over omega, omegas cancel, and we're left with cosine of pi, which is -1. So similar to the previous problem where we said it was going counterclockwise using the right-hand rule from positive to negative, we can say the exact same thing since we are going from a positive to negative. So we're going to say, again, counterclockwise, positive to negative, and again using the right-hand rule. So we'll say right-hand rule. And that is part I. They do the two different test cases they gave us. So So that is all of chapter 29, exam 29.